Okay, so now that we know a little bit about nuclear chemistry and writing nuclear chemical reactions, let's talk about half-lives. And of course, that's a term you've probably heard and already associate with nuclear processes, so we'll talk a little bit more about that. So this is the first time we'll talk about half-lives. When we talk about kinetics, which we do a very, very brief bit of lecture on kinetics later in the course, we'll also again bring up the idea of half-lives for chemical reactions. But here for the half-life of a radioisotope, we'll see that they always obey this idea of what we'll come to know as first-order kinetics. And that makes things actually easier, believe it or not, here in nuclear chemistry, that we only have to deal with that sort of behavior. So when we talk about a half-life, we're going to be talking about how long it takes to decrease the original number of radioisotopes by 1/2, and the half-life is constant, it stays the same. So when that amount of time passes again, you'll be down to 1/4 of the original sample because you'll have lost half and then half again. So although it may sound a little bit difficult, it's actually the easiest type of half-life that we can deal with. Okay, and again, now just defining that, the half-life of radioisotope is the time for the radiation level, which is a measure of the actual number of radioisotopes, to decrease or decay to 1/2 of the original value. So in our image down below, we see that we have 20 milligrams of iodine-131, a radioactive isotope of iodine that's commonly used in radiochemistry or in diagnostic imaging, as it's known in the medical setting, to look at thyroid function. So if we have 20 milligrams to start, after one half-life, we're down to 10 milligrams, and then after another half-life, we're down to 5 milligrams, and then another half-life, we're down to 2.5 milligrams. So it's a constant amount of time that continues to decrease the amount of sample before the half-life to half after the half-life has gone. And if we go through multiple half-lives, we see after one half-life, we're down to 50%. After another half-life, we're down to 25% of the original sample. And then after a third half-life, we're down to 12.5% of the original sample. So it's a very predictable way to follow amounts, and for something like a medical radioisotope, we certainly want it to be a short half-life. We don't want to expose the patient to very much of that radiation, so we want to pick something that gives a relatively safe and short exposure. And here's another way of representing this idea. It's known as a decay curve, and a decay curve shows the decay of radioactive atoms and the remaining radioactive samples. So we see here at the start, at time 0, we have basically all of the radioactive iodine-131. None of it's decayed into its daughter nuclides, as they're known. After about 8 days, which is about the half-life for that radioactive iodine, which again is pretty short, so it doesn't linger in the body very long. It's enough time to do the diagnostic imaging that's needed, and then it's eliminated in relatively short order. So we see after 8 days we're down to half, and then half again, and finally we see 5 half-lives here. After a little more than that, a few more half-lives, we're essentially down to none of the original sample. Of course, if you know Zeno's paradox, you know that if you're always decaying by half, you're never going to get to 0. But ultimately in radioactive isotopes, there is a point at which the last isotope decays and you don't have any of the radioactive isotope left. So we don't have to worry about the fact that if you always cut something in half, you'll always have a half left. Actually, with atoms, there is a point where you will completely use up the sample. So we've been very conceptual so far in this chapter on radioactivity and nuclear chemistry, but now we do have something that we can do some calculations on, and half-life calculations will allow us to determine either how many half-lives have passed or how much of our samples left after some amount of time. And so we can ask that in a way that doesn't even have to have an integral number of half-lives. If I get really tricky with the questions on the homework set or the exam, I can ask things that maybe are 2.5 half-lives or some such thing. So again, if we're looking at a single half-life, we have an amount, in this example 40 milligrams of radioisotope to start, so there would be 20 left after one half-life. After 2 half-lives, now that 20 milligrams goes down to 10 milligrams, and so it's pretty easy to follow. The math here is very simple because we're using whole numbers and whole numbers of half-lives, but it's the same sort of idea no matter if we do simple half-life calculations like this, or if we try to get a little more complicated, as you'll see here in a moment. So we see that decay curve again with the iodine 131, and now we're just looking at the fact that we start with 20 milligrams. After each half-life, we'll decrease by half, so after 8 days we'll be down to 10 milligrams, 16 days we're down to 5, 24 days we're down to 2.5, and then we're down to 1.25 milligrams after 4 half-lives, and 0.625 milligrams after 5 half-lives, so on and so forth. So it's pretty easy to determine those if you've gotten the hang of this half-life stuff. So let's follow up with a sample calculation, and then we'll do a learning check. Okay, so a sample calculation of half-lives. Here we have phosphorus 32, a radioisotope used to treat leukemia, has a half-life of 14.3 days. If a sample contains 8.0 milligrams of phosphorus 32, how many milligrams of phosphorus 32 remain after 42.9 days? So we'll use our stepwise approach that we've used in the past for attacking problems like this. And number 1 is to state the given and needed quantities. So we're given that it's 8.0 milligrams of phosphorus 32 to start. We're told that it's a half-life of 14.3 days, and we see that we have 42.9 days that have elapsed. So that leaves us with what we need. Our desired answer is the number of milligrams of phosphorus 32 remaining after those 42.9 days. So now we're on to step 2. We're going to write our plan to calculate that unknown quantities. So we're going to convert days, knowing the number of days in a half-life is 14.3 days, into the number of half-lives that have elapsed. And then we're going to be able to take that starting number of milligrams of phosphorus 32 and convert it into the milligrams remaining of phosphorus 32 after that many half-lives have elapsed. So in our next step, here we are, step 3, we're going to write the half-life equality and conversion factors. So if one half-life equals 14.3 days, then we can represent that as a fraction where we have either 14.3 days over one half-life or the inverse, one half-life over 14.3 days. Now we're on to step 4, where we're setting up the problem in a way that will allow us to calculate the needed quantity. So we're looking for the number of half-lives here, which means we're going to take that 42.9 days that has elapsed, and we're going to need the 1 half-life over 14.3 days form of that conversion factor. And when we multiply through, we see that we have 3 full half-lives that have elapsed. So if we started with 8 milligrams, after 1 half-life, we would have 4.0 milligrams. Remember, 8.0 to start. Keep those sig figs in mind. The 3 for the 3 half-lives is actually 3.00 because of the 42.9 days and the 14.3 days. So we're down to 2 sig figs now because of the 8.0 milligrams of phosphorus 32 to start, which goes down to 4.0 milligrams rather after 1 half-life. And then another half-life brings us down to 2.0 milligrams. And then finally, after that 3rd half-life, we're down to 1.0 milligrams of phosphorus 32. Okay, and so as you recall from the radioactive iodine that I mentioned was used to diagnose thyroid disorders, and then the radioactive phosphorus that we just worked together to find that we'd have 1.0 milligram left after that many days, is used to treat cancer, leukemia specifically. Here's a table in our text, table 4.7, that lists the half-lives of some common radioactive isotopes. And again, radioactive isotopes that are either naturally occurring tend to have very long half-lives, like the carbon-14, potassium-40, radium-226, strontium-90, uranium-238. These naturally occurring radioisotopes have very long half-lives, something on the order of thousands to millions or billions of years, whereas the ones used in nuclear medicine tend to have very short half-lives, as we see with the chromium-51 or the iodine-131. These are typically used for specific purpose. If it's to treat cancer like phosphorus-32, then it's a very short-lived half-life. You want to dose those cancer cells quickly with the radioactivity, but not have it linger so that it affects the normal, healthy cells. Iodine 131, of course, you don't want that to stick around too long and impair thyroid function instead of diagnose thyroid problems in the first place. So that's why we tend to have that very big disparity between what occurs in nature and what we use in nuclear medicine. Okay, so we looked at a problem, and as promised, we're going to follow up here with a learning check. So in our learning check, we're told that the half-life of iodine-123 is 13 hours. How much of a 64 milligram sample of iodine-123 remains active after 26 hours? So this is a very similar approach to our practice problem. We're going to use those various steps, and hopefully, if you're really good at this and you've already caught on to how these things work, you've already selected the correct answer. But otherwise, pause the video, take your time, work through those steps like we did for the sample problem, and then we'll check in and see how you did. Okay, so just like our sample problem, we'll state the given and needed quantities and analyze the problem. So in this case, we're given that 64 milligrams of iodine-123 is our starting amount. We're told that one half-life is equal to 13 hours, and we're told that we need to know how much has remained after 26 hours. So we're given that it's 26 hours is the time of interest, and then what we need is the milligrams of iodine-123 remaining. Okay, so on to our next step. Step 2, we write a plan to calculate the unknown quantity. So we've got to find a way to convert the 26 hours that has elapsed into a certain number of half-lives, and to figure out how those half-lives have impacted that 64 milligrams to start to give us the amount remaining, which is really what we're looking for here in the problem. Okay, step number 3, write the half-life equality and conversion factors. So we know that one half-life for this radioactive iodine isotope is 13 hours, and either we could represent that equality as a conversion factor with one half-life in the numerator and 13 hours in the denominator, or the inverse, 13 hours in the numerator and one half-life in the denominator. So if we're going to look at 26 hours to start, we're probably going to need that form on the left that has the one half-life over 13 hours. Okay, and here we see step 4, set up the problem to calculate the needed quantity. So the number of half-lives that have elapsed equals that 26 hours, and just like I said in the previous slide, we're going to want the form one half-life over 13 hours. When we multiply through, we see that that gives us 2 half-lives, and therefore if we have 64 milligrams to start, after one half-life has elapsed, we're down to 32 milligrams. And then after another half-life has elapsed, we're down to 16 milligrams, which was answer choice B. So hopefully these aren't too bad. They're very regular. Once you get used to the pattern, they tend to be very easy to follow sorts of examples. And I tend to stick with, at least for this part of the course, the integral number of half-lives, although like I said, when we get to kinetics, we'll talk about half-lives again, and things can get a little more complicated there. But for now, if you look at the homework set questions, you'll see that they tend to involve a certain whole number of half-lives, and That's what you'll expect on the exam as well for this early chapter here, where we talk about nuclear radioactive isotopes and half-lives. Okay, so not such scary math. Hopefully getting familiar if it is not working out for you yet after the sample problem and now this learning check. Please do go ahead, work some additional practice problems in the text, and reach out to me if it's still not coming to you, because it does take some getting used to and a fair deal of practice if you haven't done these half-life calculations before. Otherwise, if things are going well, then we'll meet each other again in the next section of Chapter 4.